before going to CUDA code directly and seeing the compilation, we're gonna see here, I have an example of vector addition. I already have this code. So in order to generate a PTX file that is our intermediate representation for CUDA, we're gonna see that we need here to compile the code with the flag of PTX with vector addition. Well, we're gonna call the CUDA code, and we just run this, and here is gonna generate our vector addition PTX. So we can see here some of what's going on in under the hood. We're gonna see that we have the version here of PTX. We have the version of our streaming multiprocessor. We have our address size. We have the entry that we have here, our kernel with the different parameters. In this case, if we go to the to CUDA, we see that we have 4 parameters. So we can see here in PTX we have these 4 parameters. We see here that we have our predicate in this register. We have this 4.32 register as well. And here we see more of the code. This will be to calculate the index, the EDX that we have here. So in order to calculate this, we do the multiply addition operation that we saw earlier, is storing this with the sin32 variable with using the lowest bits, storing here in the register R1 the result. We have the tensor ID, the number of blocks, and the the block dimension and the block ID. And then here we'll see more of the operations that we have in code. This is what we saw in the previous lessons, the basic details. Uh, so here we already saw how to like see the and visualize the assembly code all based on our CUDA code. Um, we're also, if we want to compile our binary in here in this code, we just have to run it like this without the PTX um, flag, and we will have our binary output that we could run here, and we could see the output of our um, program. If we wanted to indicate a specific output for this, we will specify the output with minus O flag and output for the vector addition, and then we will just execute this program to have the same result. We're gonna see some considerations in this code. We're gonna see something about memory coalescing, where a good scenario that we could have is when the different threads are accessing contiguous address in memory, as we can see here. Something that will be bad, where this will be our ideal case, but something that would be degrading is the case where we have random addresses in our code. So we have, like, for example, like a linked list where we have scatter patterns of addresses in our different elements in the linked list. That will hurt the performance as the warps they work like in groups of 32 bits, and that will degrade the performance. We will have to, for example, go through different random addresses like it will be here, there will be scatter in the memory, and this will cause like a lot of cache misses where the cache in our GPU and the RAM and the VRAM is less than our cache in our CPU. Something else about this is the occupancy. where the occupancy is the number of active threads per streaming multiprocessor. Where we have higher occupancies, the better performance. And so we have to remember that where higher occupancy implies better performance. Related to this, we have register usage, where too many registers reduces the occupancy. One last instruction that we're gonna see in our PTX code is bar and sync 0, that is for synchronization. In our CUDA code, we use the synchronization. See, we use here in order to synchronize the different threads to have like a synchronization in all the reading and writing in the registers and avoid race conditions. So in our PTX code, we will see something like sync in this case. Well, in this case, we don't see it, but sync is in order to synchronize the execution.